Thank you very much. Thanks. Yeah, really thank Libo and Ricardo for inviting me, and also all the secretaries and the students putting a lot of hard work behind the scenes. And then I used to be here, so I acknowledge this inspiring environment here as well. And it's been really nice to be back in Mainz. So yeah, they also kind to put me right after Alex. So I don't really have to, I guess, talk much about the spin waves. So okay, he had very good introduction. So yes, I'm also studying spin waves here. But the spin waves I talk about here is driven by dipole-dipole interaction. Well, what is dipole-dipole interaction? It's something super classical, and perhaps everybody has seen something like this somewhere. So it's just an interaction between two magnetic moments. So say these are two small microscopic spins in a magnet. And then, okay, one of them, of course, makes a static dipolar magnetic field. And then this exerts torque on the other. And then, of course, the other way around. So this is, this is what you usually call dipole-dipole interaction. And then I'm going to talk about ferromagnets mainly. Okay, it can be ferrimagnets, but okay, it doesn't matter. So these interactions are long-ranged. So that means, okay, it affects essentially the entire sample. So it's a bit difficult to handle, but I discuss a small fluctuation on this ferromagnetic ground state driven by this dipole-dipole interaction. And then, okay, exchange interaction, for example, Jaroszewski-Moria, okay, yeah, you can include these things, but I'm not going to discuss these things because it's long-ranged. In the limit of a large sample with long wavelengths, this thing always dominates. So I kind of ignore all the other things. And then it's known that in this regime of long-range spin waves in a ferromagnet, it's been known for ages, since 1960s, that there is a surface spin wave. So say you have a slab of magnet like this, magnetized in this direction, and then there's a surface wave propagating in these. And then the main feature, important feature of this is this mode is chiral with respect to the direction of the magnetic moment. So when the magnetic moment is pointing up, okay, say it's propagating only in the counterclockwise direction, while when this magnetic moment is flipped, okay, this chiral direction also flips. And then it's robust in the sense that, okay, it's not caring too much about the kind of magnet. As long as it's ferromagnet or ferrimagnet, it's always there. It doesn't matter if it's metallic insulator, disorder, it doesn't matter. And then the shape of the sample, it doesn't matter. You can have a sphere, you can have a cylinder, you can have a box. Anything is fine. You always see this kind of mode. And this is experimentally observed. And also, recently people were speculating because of this robustness, they could be topological. And they put, say, for example, an obstacle at the surface, whose size is of the scale of the wavelengths. Still, okay, this mode goes around the obstacle without scattered. So there was a speculation, because it sounds very much like, say, topological edge states of the quantum Hall effect. But there's one major problem. So this is the band structure, bulk band structure of this dipolar spin waves. Okay, I'm just showing this kz equal to 0 slice. And then, okay, but the details really don't matter. I put this magnetic moment in cubic lattice, and I just plotted the band structure. The details really don't matter. So the only important thing is that there is only one band. Of course, because we have only one magnetic moment per side in the cubic lattice, so of course there should be one band. But then, okay, how come there's anything topological? There's only one band. And on top of that, so the frequency at which this mode appears is actually above this bulk band. Okay, as I said, okay, so let's say, you cut the surface perpendicular to the, along the x direction, so surface perpendicular to the x direction. Then, of course, you see the edge states in the y direction. And then, as I said, it's chiral, so if you cut the surface on the positive x side, okay, you get maybe, say, positive k, and then the other side, negative k. But anyway, it appears above the bulk band. So, okay, it's not a gapless state. So of course, the question then, is it topological or not? So I answered this question in a positive way. But I have to warn you that there's nothing useful here. So I just showed this is topological. But on one hand, it's not going to change the experimental status of this mode. So it's being studied for ages, very well understood. And then application-wise, okay, there has been already a lot of effort. And this is not going to help any application. And on the other side, this doesn't give you any new topology. So topology I'm going to talk about is really within this tenfold way. And it's relatively simple. And is it going to be extended in some way to other waves? In my opinion, it's unlikely. So it's just for fun. That's what I have to warn. And then, okay, so there are two steps, right? So I first show you that there's something topological about this system. So this part is relatively simple from this tenfold classification perspective. So I'm going to be quite brief. And then the second part is about why the mode doesn't appear in the gap. And this part, okay, I have to show you some equations. I'm quite sorry, but there's no other way I can see. And then there's a caveat. So I talk about the real system is three-dimensional. But I focus on this kz equal to 0 slice in this talk, essentially for simplicity. There are some subtleties and complications, and then the statements are much weaker for the 3D version. But the details are found in the paper. Also, the paper is much more mathematical. So here I skip many mathematical details. And then it sacrifices some kind of accuracy of the statements. But OK, you can ask questions. So OK, I first review the dipole-dipole interaction. So OK, if you write it in the formula, it looks like this, right? So in real space, OK, you have two magnetic moments at R1 and R2. And then the interactions look like this, essentially quadratic. And then you sum over all the magnetic moments in your system, all the pairs. And then, OK, I'm interested in the ferromagnetic ground state. So use this linearization. So mx, my independent small components. OK, mz is the order direction. So this is the ground state configuration. And then, of course, at the quadratic order, there's small correction to this z component. And then you put this in and then expand it at the second order. And then, OK, apply a Fourier transform in the cubic lattice, and then you get this. So this is the energy function of this dipolar spin wave. And unfortunately, because this is a long-range interaction, you cannot calculate this Fourier transform analytically. So I have to do some numerical calculations, but the results are here. So this component, which is OK, so this is 2 by 2 matrix, OK, and then this component, which is proportional to, which is a scalar, is almost constant. So the dispersion is there, but very, very weak. So OK, more or less we treat this as a constant. And then OK, these two have OK some dependence on the momentum. But you can see at the origin, looks like something is going wrong. So this is OK numerical calculation, so just matter of resolution. Well, that's actually a singularity of the Hamiltonian. So because this is long range, at the zero momentum, there's a singularity, discontinuity of the Hamiltonian. So it's an outright singularity. It's not degeneracy. And then, OK, for the time being, I call this 2 by 2 matrix here Hamiltonian. And if anybody has any doubt about this terminology, then OK, you're on the right track. So OK, so then OK, we have a Hamiltonian. So let's try to characterize this topologically. It turns out that this belongs to symmetry class C1 in the Alexander-Sermbal classification. So what was C1? OK, you have a time reversal symmetry, which is anti-unitary operator that commutes with the Hamiltonian. And then you have the chiral symmetry, which is a unitary operator that anti-commutes with the Hamiltonian. But this anti-commutation is actually, it doesn't have to be satisfied. Well, so it has to be satisfied only modulo a constant shift, because the constant is the chemical potential in the electron system, and then it's not supposed to matter. So there's a constant shift freedom for this. And then, okay, these for C1, this T and gamma must be anti-commuting. And then T square, gamma square, both square to 1. And these conditions are satisfied. And then when it's class C1, you can always put the Hamiltonian into this canonical form. So this constant part corresponds to the chemical potential in the electron case. And then you can have this matrix proportional to sigma 3 and proportional to sigma 1. And these two are real symmetric matrices because of this time reversal constraint. But this is a canonical form. You can always bring it in this form if these conditions are satisfied. And then, as you saw, okay, the dipole-dipole Hamiltonian essentially has this form, okay, approximately, because it's not entirely constant, but almost constant. Now, once you have this form, you can always define a winding number. So take any loop in the 2D case space, or 3D, it doesn't matter. You take any loop, and then along the loop, assume that these two don't become 0 simultaneously. Then you can construct this ck plus isk, and then you take the determinant of this logarithm and then integrate or along the line integral. And then this must be quantized. So this is a winding number. By the way, so in the electron language, this is important. Electron language, gapped H means this condition satisfies. So this shouldn't be 0 simultaneously if it's gapped. So in the gapped region, you can always define this winding number, right? And then whenever this winding number is non-zero, there is something inside. So there must be a singularity. Singularity here means it can be a real singularity where the Hamiltonian is not defined, or it can be simply the zero of these two quantities. And then so this winding number can detect this kind of defect. And then once defect is there, it cannot be removed by any continuous deformation of the Hamiltonian as long as these conditions are satisfied. So this is the topological stability of this. Right, so let's say, okay, you have something like this. Actually, we already saw in the dipole-dipole Hamiltonian, the origin is the singularity. So let's try to compute the winding number around the origin. It turns out to be -2. So there's something, of course, because it was singularity. And then it's -2. Okay, then what can you conclude from this? Well, okay, this is the most topological part of this talk, I think. So I do just homotopy, right? So you deform this loop continuously. You enlarge it like this. And at some point, this upper edge and the lower edge would meet at the zone boundary. And then, because they are traversing in the opposite directions, they could be annihilated. And then split into two large loops going around the torus. And then because the winding number must be conserved, okay, this has a winding number -2, but these two large loops in total have to have the winding number -2. And then because there's this reality condition, which is this T symmetry, which rates positive and negative k, these two winding numbers must be the same, which means, okay, they have to be -1, -1. And then, okay, the same argument works so across the entire case space, except for this, the line passing the origin and this trim. Except for these points, okay, all the 1D slices have the winding number +-1. Now, okay, we have okay, let's focus on this 1D subsystem. So let's take this line as a 1D system and then regard it as a physical system. And then, okay, this has winding number non-zero. And then this has chiral symmetry, as I said. And time reversal symmetry is not acting on this line itself, but it's actually mapping this line to this line. So this line itself doesn't have time reversal, so only chiral symmetry. So this is class A3. And A3 is the SSH model. You always have this SSH dangling floppy edge state if the winding number is non-zero. And then this edge state turns out to be this magnetostatic surface waves I was talking about. So this is the topology story. That's it. And then, okay, this is, of course, like wild semi-metal, right? So in the wild semi-metal case, okay, you had a singularity in the 3D space, and you had a Chern number in the 2D surface. And then 2D slices carry the Chern number. So 2D quantum Hall edge bulk edge correspondence gives you the wild semi-metal surface state. Here, that's real version, class C1 version of this. And then this is the topology story. That's it. And so any question, maybe it's a good time to.
So I have a question to the analogy. So this already behaves as a Fermi arc.
In this case, okay, in this 2D example, it's not okay, here, okay. So to explain this Fermi arc things, you have to talk about charge cancellation, right? So you have the opposite charge counterpart of this singularity somewhere. In this case, it turns out to be at this trim. So there's a kind of string connecting this and this. But if you map this string to the edge Brillouin zone, of course, you just get the entire line. So there's no arc. So essentially, it disappears in the entire 1D Brillouin zone.
The reason for that is the dimensionality?
No, it's not the dimensionality. The position of this opposite charge, if you move this opposite charge from this pi point inside, then you get this, of course, kind of terminated line, right?
So what is constraining the charge to be at the boundary?
It's not constrained. It happened to be there.
Why?
Maybe the symmetry of the system is too high. I don't know. I just put them in a cubic lattice. I haven't checked this point, actually. That's a good point. But once you, there's a caveat. So once you move these singularities away from trims, you have to split it into two because of this T symmetry. So this charge -2, if you try to split it, then you have to split it into two -1s. And then this gives you some more complicated situation.
Direct analogical file, but
yeah.
some sort of grammars file.
Yeah. Close to, yes. Okay, yeah, this is okay. A bit too far.
So famous would have shown number 1, so you couldn't split it. But here you can split this guy.
Yeah, but
the edge states actually would also have lower amount of support on the edge, right? Like there would be, they wouldn't be on all of the edge.
Yes, here, so this correspondence, this T invariance is guaranteeing that if it appears on this side, okay, it's going to appear on this side. Or actually, these two are identified in some sense. Physically, they are the same thing. I'm going to talk about this later, but
why can't I split them and also split them at the other trim and bring them together and then highlight?
That's possible. That's possible. Topologically, that's possible, but simply not happening in this system. And I don't see any way to tune this system in that way. So if you put in parameters, in some parameters, you might be able to do it. But if it's realistic or not, I don't know. Okay. So yeah. So I called that 2x2 matrix Hamiltonian, and it sounded like so, I guess, for most people. But in fact, it's not really the case, it turns out. So to explain the situation, I have to look back at what you say you call Hamiltonian in the electron physics. So you have the energy, and then it's quadratic in these operators. I'm sorry, somehow I made it into the PDG format, but it doesn't have to be. But okay, you have some Hermitian matrix here, which is called Hamiltonian in this context, right? And then if you write down the Schrödinger equation for this system, you get something like this. So this matrix appears as essentially time evolution operator acting on this vector space. Then it's immediately clear from this equation that the eigenvalues of H correspond to the eigenfrequencies of the system. And on top of that, okay, eigenvectors of this H are really the eigenstates of the physical system. So okay, that's why you study the eigenvalues, the spectrum of H, and then talk about spectral gap. Okay, it all makes sense. So okay, we have something very similar formally. So we have the energy, and then we have the magnetic moments quadratic, and then you have a symmetric 2x2 matrix. In this case, 2x2, but a symmetric matrix here, H. And then I call it Hamiltonian, and many people do. But this is a classical system. So if you write down the equation, the motion, it looks like this in this case. So this gamma is an irrelevant constant, and then mu is the magnetic moment. It doesn't matter in this talk. And then you do get this H times this vector, but with an extra factor, extra matrix of this form. So because of this form, this matrix form, okay, even if you have eigenvalues and eigenstates of this H, it doesn't necessarily mean you have eigenfrequencies and eigenstates of physical eigenstates of this system. So that's the issue. So from this, okay, studying the topology of H doesn't make sense because, okay, okay, we saw something topologically non-trivial here, but as it is, okay, it doesn't directly relate to any physical quantity. But somehow it turns out, okay, so this thing is quite important. I call it J, and then you should remember this form now. And then this J is an incarnation of classical mechanics Poisson bracket. And then this structure plays a very important role. And then because of this structure, somehow in this particular case, in class C1, I'm going to talk about these eigenvalues of H and eigenvectors of H are directly related to the physical eigenfrequencies and the physical eigenstates. That doesn't always happen. Okay, so to understand this point, okay, I just have a short review of the classical Hamiltonian mechanics. So Hamiltonian mechanics is defined on the canonical coordinate space P and Q. And then there's a Poisson bracket structure predefined into the system. So okay, the two functions f and g of PQ, and then okay, you define the Poisson bracket of the two like this cross derivative. And then using this, Hamilton's equations of motion can be written in a nice way. So it's Poisson. The time evolution of Q is a Poisson bracket of Q with the energy, which looks like, of course, this. Okay, partial derivative by P, and then like this for P, right? So it's quite symmetric. But there's this sign +1 and -1, and it's kind of cross Q to P and then P to Q. So this is precisely what this is. So when the energy is quadratic in P and Q, so it's like this, then okay, this is precisely representing this Poisson bracket structure. So roughly speaking, what you want is the eigenstate of J times H, because that's precisely corresponding to the time evolution operator. So that's the physical eigenstates, not the eigenstate of H. That's not what we are interested in here. And then in the spin system, it turns out that this x component of the magnetization is the momentum, and the y component is the coordinate. So in this, if you do this identification, that spin system is precisely classically a Hamiltonian system in this sense. Right. So I said that the dipolar Hamiltonian belongs to class C1. Class C1 meaning, okay, you have two operators, T and gamma, which satisfy all these conditions. Whatever they are, it doesn't matter. They do exist. And then, okay, mathematically, that's class C1. But here, they have specific meanings. First of all, T here, of course, this is not the physical time reversal T, because, of course, this is magnetic ferromagnet, so T is broken. So this T is not the physical time reversal symmetry. But it's simply the fact that, okay, we are handling a classical system, which is real. So trivially, there's a reality condition. So complex conjugation is just a T. So it simply says, okay, this is a classical system. And then, okay, now this chiral symmetry. As I said, chiral symmetry has to be satisfied only modulo shift by constant. So in this case, H minus D, this part, anti-commutes with that J, which is this anti-symmetric matrix, because, okay, sigma 3 and sigma 1. So this looks like, essentially, this is sigma 2. So they anti-commute quite obviously. So this J, which was the Poisson bracket, is essentially acting as a chiral symmetry operator. So this is crucial. So the point is that, okay, in this dipolar Hamiltonian, as formally, it's in class C1. But it's not just that. These two defining symmetries are directly related to the classical mechanical structure of the original problem. So T is the reality condition of the classical system, and then gamma is the Poisson bracket, which is defining the classical dynamics. And then in this particular case of class C1, we call it class C1 star for just convenience, okay? So in the end, okay, precisely speaking, okay, this dipolar Hamiltonian belongs to class C1 star. Now, in this class C1 star, you can prove that basically the eigenvectors of H directly correspond to the eigenstates, physical eigenstates. So I have to do some algebra, and then it's not so hard. So just Hope you can follow. So okay, let's take any eigenvector of this original Hamiltonian H. So this is not necessarily a physical eigenstate, okay? Then labeled by n plus somehow, and then which belongs to this eigenvalue d plus epsilon n. So okay, so this d is of course the constant part. So this epsilon n is related to this c and s. And then in the quadratic case, if the quadratic means if the Hamiltonian is 2 by 2, then okay, this epsilon n is simply square root of c and s squared. Now, okay, you define this another vector v n minus by multiplying this by this j, Poisson bracket. And then because of this anti-commuting condition, you can easily show that this n minus also is an eigenvector belonging to an eigenvalue d minus epsilon n. So it's a partner of this n plus. And then because j is antisymmetric, these two vectors cannot be linearly dependent. So they are, in fact, they are orthogonal to each other. So okay, we have two linearly independent vectors with these eigenvalues. So all the eigenvectors, this means okay, so I took an arbitrary eigenvector here. So that means all eigenvectors of H with this condition come in pairs with these eigenvalues. And then because of this, okay, you can always choose this epsilon n to be positive, right? It's just a matter of convention. Okay, so they are essentially all the eigenvectors of this H. And then heuristically define this another vector u, which is complex now, by this formula. And then you can show that this u is an eigenvector of JH, which was the relevant thing for the physical eigenstates. And then this u belongs to the eigenvalue of JH given by this I times square root d square minus epsilon n squared. So this u represents the physical eigenstates. And then this thing here turns out to be the physical eigenfrequency. So there's direct correspondence between this v and the u. And then say if v is localized at the edge, okay, of course this vn minus also is localized, so u is also localized. So then, okay, if you get the bulk edge correspondence of this h, you immediately get the edge states for jh. So that's essentially the end of the story. But okay, I still have to explain why the frequency is above the band gap, sorry, above the bulk band. Okay, so what are the bulk eigenstates in this context? So Hamiltonian, as I said, has the eigenvectors like this in this pair. And I already mentioned this. So gapped H in the usual sense, electron sense, means this epsilon non-zero. But we already saw that classical eigenfrequency of this H corresponds to this quantity, d square minus epsilon square. So this is always smaller than d if epsilon is non-zero. So meaning if the bulk is gapped, what this means is this classical eigenfrequency is always smaller than d. So this d, which was chemical potential for electrons, in this context is actually a maximum value of the eigenfrequency you can take in this classical system. And then, okay, if there's something non-trivial topologically for H, and then, okay, you predict an edge eigenvector for H appearing in the gap of this H, meaning this epsilon 0. So its eigenvalue is going to be d, exactly. And then, okay, I already showed that, okay, you can define the eigenstate of JH from this V, so U. And then this is going to have, oh, sorry, I think I is missing. It's plus minus I times d. So the edge mode eigenfrequency is going to be exactly d, which is, of course, bigger than any of these bulk. So that's why it appears there. And then this is the end of the story. OK, so that's it. So, okay, I showed that classical dipole Hamiltonian is in the class C1 in the usual tenfold way. And then what's special about this particular case is that these defining symmetry operators have some physical meanings in the classical mechanics. So T is a reality condition, and then gamma chiral symmetry is a Poisson bracket. So in this case, in this particular case only, eigenstates of the classical Hamiltonian. Okay, so yeah, in general, what we classically call Hamiltonian doesn't have eigenstates which are directly related to physical eigenstates. But when this condition is satisfied, okay, in the end, there is a direct connection between the two. So the bulk edge correspondence of this Hamiltonian is actually the bulk edge correspondence of the real physical eigenstates. And then the predicted eigenstates in this case have somehow the eigenfrequencies above the bulk band because of this, this particular correspondence. Right, I want to acknowledge my collaborators at different stages of this work. I've been helped by many people, but in particular, I want to mention the first two. So Guo Chan is a mathematician, and I really needed his input to put all this structure in place and make sure that everything is consistent, and he was very helpful. And also Philip, he's an experimentalist measuring all these spin waves. And then he has a really good working knowledge of this dipole-dipole interaction, which is long range, so it's very difficult to see if you're just looking at the equations, what the physical consequences, and then it was very important that he contributed to guide me physically through the problem. Yeah, and thank you very much for your attention.